Hello everyone, welcome to my project presentation. Today I am going to explain my project, design and implementation of dual board flight controller system and telemetry system for Delta Wing UAV using Stm32 microcontrollers. Delta Wing UAV are known for their high speed and structural simplicity. However, controlling them is quite challenging because they use combined control surface called elevons which manage both pitch and roll at the same time. In this project, I have developed a compute dual board flight controller system using STM32 Blue Pill microcontroller. This architecture separates real-time flight stabilization and telemetry and monitoring tasks, result in better performance and easier debugging. The system consists of two STM32 boards. First one is board 1. These boards handles all time critical operations. It reads data from the MPU 6050, applies complementary filter to accurately calculate pitch and roll angles, processes input signals from the fly sky receivers, run a PID controller for stabilization, perform proper elevons mixing for the delta wing, and generate pulse with modulation signal for the two servos and brushless ESC. And second board is board 2. This board receives real-time flight data from board 1 through UART communication. It integrates GPS information for positioning and timing, and display all important parameters such as pitch, roll, altitude, throttle, servo position, and PID values in a clean and readable format on the serial monitor. The communication between both boards happens at 57,600 baud rate using UART, ensuring fast and reliable data transfers. The main component used in this project are two STM32 Blue Pill microcontrollers, MPU 6050, BMP 280 barometer, and fly sky receiver. For manual control, input two servos for controlling the elevons, brushless motor with ESC for GPS module connected on board 2 for live positioning and time data. All modules share a common ground, which is essential for stable I2C and UART communication. The servos and ESC are powered from a separate 5-volt source to avoid noise on the microcontroller. On board 1, the MPU 6050 provide raw accelerometer and gyroscope data. Complementary filter is used to combine this data and produce smooth, drift-free pitch and roll angles. They receive the receiver inputs are converted into desired set points. The PID controller then calculate the corrections value based on the error between the desires and actual angle. These corrections are mixed according to delta wing eleven logics. Left eleven command equal to pitch PID plus roll PID, and right elevons command equal to pitch PID minus roll PID. The final PWM signals are sent to the servos and ESC. At the same time, board 1 sends all flight parameter to board 2 via UART communication, and board 2 receives this data, parses it, combines it with GPS coordinates and the time, adjusted for Indian Standard Time, and displays everything clearly on the serial monitor in a user-friendly format. During extensive ground testing, the system performed very well. The PID controller provided smooth and stable pitch and roll stabilization. In the future, this project can be extended with several advanced features such as altitude hold mode using BMP 280 and feedback Kalman filter for even better sensors. Fusion wireless telemetry using SC05 or LoRa return to home and autonomous waypoint navigation.